modern physics stands in a position no earlier scientific framework ever reached. Its predictions do not merely resemble observation, they coincide with it to extraordinary precision. Equations written decades ago continue to forecast experimental outcomes with agreement so exact that deviations smaller than a billionth are measurable and meaningful. This level of accuracy is not accidental. It is the defining feature of physical law as it exists today. Scientific strength is operational rather than philosophical. A theory earns credibility by predicting results before they are observed, and by surviving repeated confrontation with increasingly precise measurement. Modern physics has passed this test relentlessly. From atomic spectra to planetary motion, from particle collisions to gravitational waves, the same mathematical structures continue to hold. Their success is cumulative. Each confirmation tightens confidence. What has changed is the scale of precision. Experimental tools now operate in regimes once thought inaccessible. Distances smaller than the internal structure of atoms are probed routinely. Time intervals shorter than a single oscillation of electromagnetic radiation are resolved. Energy differences so slight they were once dismissed as noise are now central signals. Measurement no longer blurs theory, it interrogates it. As precision increases, tolerance disappears. A theory that once matched observation within generous margins is now required to align across many independent measurements simultaneously. Small discrepancies can no longer be absorbed into uncertainty. They must be explained or eliminated. Precision transforms convenience into constraint. This is where success becomes demanding. The laws of physics have not failed. Objects continue to move as predicted. Fields behave as expected. Particles interact exactly according to established rules. What emerges instead is tension between different descriptions that are each individually successful. Each framework works. The difficulty arises when they are required to coexist within a single, universal account. This distinction matters. An experimental failure occurs when observation contradicts prediction. A theoretical tension occurs when multiple correct predictions cannot be derived from the same assumptions without adjustment. Modern physics is dominated by the second case. The universe behaves consistently. Our descriptions struggle to remain mutually aligned under extreme scrutiny. In earlier eras, limitations were hidden by imprecision. Approximations were sufficient because experiments could not resolve their consequences. Today, those consequences are visible. Assumptions about scale separation, background stability, and negligible effects are no longer abstract choices. They are testable commitments. Precision forces them into the open. Nothing in this process suggests that physical law is breaking. The universe shows no instability, no erratic behavior, no deviation from consistent rule-governed evolution. What is strained is coherence across frameworks that were developed independently, each optimized for a particular domain. Precision now forces those domains to overlap. This is the defining feature of the present moment in physics. Not ignorance, but exposure. Measurement has become sharp enough to reveal where agreement is assumed rather than guaranteed. The closer predictions approach perfection, the less forgiving inconsistency becomes. Theories that once appeared seamlessly unified now show stress at their boundaries. Not because they are wrong, but because they are being asked to do more than they were constructed to do. Success has pushed them into regimes where alignment is no longer automatic. As measurement continues to refine reality, the challenge is no longer explaining isolated phenomena. It is maintaining internal consistency across all verified observations at once. And it is precisely here where success becomes pressure that the limits of current understanding begin to appear. As theories are pushed harder, the nature of disagreement changes. It no longer appears as a dramatic mismatch between calculation and experiment. Instead, it emerges as a subtle misalignment between frameworks that were never designed to be compared at this level of detail. Each framework passes every test placed before it within its intended domain. The difficulty arises only when precision forces those domains to overlap completely. Modern physics relies on layers of description. Each layer abstracts away details that do not matter at a given scale. This strategy has been extraordinarily effective. It allows complex systems to be described with manageable mathematics while retaining predictive power. For decades, this layering worked because experiments rarely demanded full cross-compatibility. A theory could succeed locally without being globally consistent with every other theory. Precision has ended that luxury. Measurements now tie together phenomena across enormous ranges of scale. A parameter measured in one context influences predictions in another. A correction introduced to improve agreement in one regime propagates into many others. Theories are no longer isolated tools. They form an interconnected system. This interconnectedness creates pressure. When two descriptions rely on incompatible assumptions, precision amplifies the conflict. An approximation that was once harmless now leaves a measurable signature. A boundary that was once conceptual now becomes quantitative. The theory does not announce its own limit. Measurement does. It is important to be precise about what kind of problem this creates. There is no observation that demands the abandonment of physical law. There is no experiment that shows nature behaving inconsistently. The tension exists only within the structure of explanation. The universe remains coherent. Our attempt to describe it as a single unified system encounters resistance. This resistance is not uniform. It appears only where theories must be stitched together. Within their own domains, they remain extraordinarily accurate. This is why the present situation is often misunderstood. It is tempting to frame these tensions as failures. In reality, they are signals of overextension. Precision reveals where a framework is being asked to explain phenomena that depend on assumptions it does not control. It reveals where a description that works beautifully in one regime becomes brittle when applied universally. This brittleness is not accidental. It is a consequence of how the theory was constructed. The success of modern physics created a sense of completeness. As predictions grew more accurate, confidence grew that the underlying structure was final. Precision has now reversed that intuition. It shows that accuracy does not guarantee universality. A theory can be exact and still limited. This realization changes how problems are interpreted. When two independently verified methods yield incompatible conclusions, the issue is not which one is wrong. The issue is whether the framework connecting them is sufficient. Precision removes ambiguity. It demands consistency without exception. This is why modern tensions cannot be resolved by adjusting a single parameter or refining a single experiment. They involve relationships between different parts of theory. Fixing one inconsistency often introduces another. Precision ties everything together. The present challenge is therefore structural rather than local. It concerns how different descriptions relate, overlap, and constrain one another. The universe does not resist explanation. It resists oversimplification. As measurement continues to improve, this pressure will not fade. It will intensify. The more accurately we observe, the more demanding coherence becomes. And it is within this demand that the true boundaries of current theory are revealed. The final consequence of this situation is a shift in how limits are recognized. In earlier eras, limits appeared when predictions failed outright. Today, limits appear when predictions succeed too well. When accuracy becomes extreme, even minor conceptual mismatches become physically meaningful. Precision turns philosophical discomfort into empirical constraint. This shift explains why modern physics feels simultaneously powerful and incomplete. Every confirmed measurement strengthens confidence in individual frameworks. At the same time, it narrows the space in which those frameworks can be reconciled with one another. Agreement within one domain tightens demands in all others. Precision acts as a binding force. This binding force exposes assumptions that once went unnoticed. Background independence, scale separation, and neglect of small effects were never universal truths. They were practical strategies. As long as experiments did not probe their consequences, these strategies remained invisible. Now they are tested directly. Importantly, nothing in this process implies that nature is inconsistent. The universe does not behave differently depending on how it is measured. Physical processes proceed smoothly across scales. The tension arises only when our descriptions are required to maintain internal alignment across all scales at once. This is the operational meaning of weakness in this context. It is not a flaw in reality. It is a point where current theory cannot simultaneously account for all verified observations without strain. Each observation is correct. Each theory works where it applies. The difficulty lies in universal coherence. Recognizing this distinction is essential. It prevents the misinterpretation of tension as failure. It frames unresolved problems as boundaries rather than breakdowns. Boundaries are not signs of collapse. They are markers of where deeper structure is required. The history of physics shows that such boundaries are not accidental. They appear only when understanding reaches a level where approximation is no longer sufficient. Precision creates them, and precision is the product of success. As measurement continues to sharpen, more such boundaries will appear. They will not signal instability in the universe. They will signal that our descriptions are approaching the edge of their domain. This is how progress begins. Not with contradiction, but with constraint. Not with failure, but with success pushed to its limit. The behavior of the universe is governed not only by laws, but by numbers embedded within those laws. These numbers do not describe size, distance, or time directly. They describe ratios. They are dimensionless quantities that compare strengths, masses, and scales without reference to human units. Because of this, their values are not artifacts of measurement choice. They reflect relationships intrinsic to nature. Several of these numbers control how the universe evolves. They determine how strongly forces compete, how matter clumps, how rapidly stars ignite and burn, and whether complex structures can persist over cosmic time. What makes them significant is not their existence, but their sensitivity. When these values are altered within the equations that describe physical processes, the resulting behavior of the universe changes dramatically. This sensitivity is not speculative. It follows directly from applying well-tested equations under slightly different parameter values. Change. The relative strength of interactions by a small amount and stable atoms fail to form. Adjust mass ratios modestly, and nuclear reactions in stars either cease or proceed explosively. Modify expansion-related parameters slightly, and matter never condenses into galaxies. These outcomes are mathematical consequences, not philosophical interpretations. Modern experiments and observations measure these constants with extraordinary precision. Particle accelerators constrain interaction strengths. Atomic clocks fix ratios of fundamental quantities. Observations of relic radiation, large-scale structure, and stellar populations converge on tightly bounded values. Independent methods, operating across vastly different scales, repeatedly identify the same narrow ranges. This situation is often labeled fine-tuning, but that phrase easily misleads. In physics, fine-tuning is a descriptive term. It does not imply intention, purpose, or explanation. It simply states that outcomes depend, sensitively, on parameters whose values are measured rather than derived. The theory does not predict the numbers. It accepts them as inputs. Nature determines the result. Crucially, sensitivity alone does not indicate weakness. Many physical systems are stable precisely because they operate near boundaries. Sensitivity can amplify structure rather than destroy it. A balance that appears delicate mathematically may be robust dynamically. The universe itself shows no sign of fragility. It persists, evolves, and structures itself reliably over billions of years. The issue emerges only when sensitivity intersects with precision. When parameters matter this much, agreement between independent measurements becomes unforgiving. A small discrepancy that would once have been irrelevant now carries physical significance. Sensitivity transforms disagreement into stress. At this stage, no conclusion follows beyond observation. The universe appears balanced on numbers that matter greatly. That balance is an empirical fact. It does not yet imply explanation, design, or failure. It simply defines where precision has placed the burden of consistency. The danger lies not in acknowledging this sensitivity, but in misunderstanding what it does and does not imply. Physics draws a sharp boundary between description and explanation. To say that outcomes depend strongly on certain numbers is not to say why those numbers take the values they do. It is merely to state that if they were different, the universe would behave differently. That statement carries no causal weight by itself. For this reason, fine-tuning functions as a diagnostic rather than a conclusion. It highlights where a theory relies on inputs that are not fixed by deeper principles within the framework. Historically, this situation has occurred many times. Quantities once treated as arbitrary were later shown to arise from underlying structure. But that outcome is not guaranteed. It cannot be assumed in advance. It must be demonstrated empirically. What precision has changed is the rigidity of constraint. Many of the same constants appear across different domains of physics. Nuclear reactions, stellar evolution, and cosmic structure formation all depend on overlapping sets of parameters. A value inferred from one context must remain compatible with all others. Precision binds these domains together. As uncertainty shrinks, flexibility disappears. A parameter that could once vary within a wide range without consequence now occupies a narrow corridor. Within that corridor, independent measurements must overlap. When they do, sensitivity remains a neutral feature. When they do not, sensitivity amplifies the conflict. This is why fine-tuning becomes physically relevant only in the presence of disagreement. Sensitivity alone does not signal weakness. It signals importance. Weakness appears only if different methods demand incompatible values for the same parameter. At that point, no amount of reinterpretation can remove the tension without altering the framework itself. Importantly, this situation does not license speculative explanations. Observational framing does not require appeal to selection effects or untested multiplicity. The data demand consistency, not narrative. Until disagreement appears, fine-tuning remains an observation, not a problem. The universe continues to behave coherently across all observed scales. The numbers governing it do not drift or fluctuate. They remain stable within measurement. Precision has not revealed instability, it has revealed constraint, and constraint changes the nature of explanation. It transforms what were once flexible assumptions into fixed requirements. Sensitivity sharpens the demand that all parts of theory speak the same numerical language. The point where sensitivity becomes decisive is where measurements fail to converge. When independent observational routes that rely on different physics infer the same number, confidence deepens. When they do not, sensitivity magnifies the disagreement until it can no longer be ignored. Precision turns numerical mismatch into structural stress. At present, most fundamental constants remain consistent across methods. This is an achievement, not a triviality. It reflects the internal coherence of physical law across enormous ranges of scale. Where disagreement does emerge, it does not hide behind uncertainty. It stands exposed as a genuine challenge. This is why numerical balance occupies a central role in modern physics. It is not because the universe appears delicately poised, but because precision has made deviation costly. A small shift now propagates widely. A correction introduced in one domain influences predictions in many others. Numbers bind theory together. Crucially, nothing in this situation suggests that the universe itself is precarious. Stars do not teeter on the edge of collapse. Chemistry does not threaten to fail. The cosmos remains stable, and long-lived. The sensitivity exists in our equations, not in reality's behavior. What precision has done is eliminate ambiguity. It has converted what once seemed like adjustable parameters into fixed points of consistency. Once fixed, those points constrain everything else. This is the sense in which numerical balance matters. It does not weaken physics. It sharpens it. It identifies where explanation must eventually deepen, not because something is broken, but because everything else works too well to allow inconsistency. Sensitivity alone does not define a weakness. But once measurements disagree, sensitivity ensures that the disagreement cannot be absorbed. It must be addressed. And that is where numerical balance stops being merely descriptive and begins to test the structure of theory itself. The expansion of the universe is not inferred indirectly or philosophically. It is measured. Multiple independent techniques quantify how rapidly space itself is stretching, and they do so using different physical assumptions, different sources of data, and different epochs of cosmic history. Each technique is grounded in well-tested physics. Each has been refined through decades of observation. Yet the values they produce do not align. One set of measurements determines the expansion rate by observing relatively nearby cosmic objects. Distances are established using astronomical sources whose intrinsic properties are well characterized through local physics. Their observed brightness, timing, or geometry provides a direct measure of distance. When combined with observed redshifts, these distances yield the present-day rate at which space is expanding. This approach is local, empirical, and repeatedly cross-checked. A second set of measurements approaches the problem from the opposite: direction in time. It examines the universe when it was extremely young, dense, and hot. Subtle patterns preserved in relic radiation encode information about the early distribution of matter and energy. These patterns are measured with extraordinary precision. When evolved forward using established physical laws, they predict what the expansion rate should be today. Individually, both approaches are remarkably successful. Each produces internally consistent results with uncertainties that continue to shrink as data improve. The disagreement emerges only when the two values are compared. The expansion rate inferred from early universe measurements is systematically lower than the rate measured using late universe observations. The difference is modest in absolute terms, but it is statistically significant. This is not a case where one method is crude and the other refined. Both are precise. Both are reproducible. Independent teams using different instruments and analysis pipelines repeatedly recover the same conflicting values. The discrepancy persists as measurements improve rather than disappearing. What makes this situation distinctive is its symmetry. Neither result is anomalous in isolation. Each fits comfortably within its own framework. The problem arises only when a single theoretical structure is used to connect early cosmic conditions to present-day observations. Under that shared structure, both results cannot be simultaneously correct. This is why the expansion rate disagreement is not classified as experimental failure. No observation contradicts physical law. Instead, it exposes tension within the framework that assumes a smooth, fully specified connection between different eras of cosmic evolution. Precision has turned that assumption into a test. As uncertainty shrinks, compatibility becomes mandatory. The universe expands in one way. Two correct methods now disagree on how fast. The significance of this disagreement lies in what it constrains, rather than what it reveals immediately. The early universe measurements depend on physics that has been tested independently in laboratories and astrophysical settings. Atomic transitions, particle interactions, and radiation behavior are all well understood within known limits. The late universe measurements rely on geometric relationships, calibrated distances, and the behavior of well-observed astronomical systems. These foundations are independent. Their disagreement, therefore, cannot be dismissed as a shared flaw. As precision has improved, many possible sources of systematic error have been examined and constrained. Calibration uncertainties have been reduced. Environmental effects have been modeled. Independent observational channels have been added, yet the gap remains. Any single adjustment large enough to reconcile the two expansion rates now disrupts agreement elsewhere. Precision has interconnected the problem. This interconnection is what transforms a numerical difference into a structural issue. The expansion rate is not an isolated quantity. It influences estimates of the age of the universe, the growth of cosmic structure, and the relationship between matter and radiation over time. Altering it affects multiple observables that are already measured with high accuracy. There is little freedom to change one piece without moving many others out of alignment. For this reason, interpretation remains cautious. Declaring the presence of new physics without necessity would risk destabilizing frameworks that work exceptionally well. At the same time, insisting that the discrepancy must vanish offers no mechanism for why it persists and sharpens as data improve. The disagreement occupies a narrow and uncomfortable space where neither dismissal nor resolution is justified. Importantly, nothing about this tension suggests that cosmic expansion is ill-defined or unstable. Space continues to expand smoothly and predictably. The disagreement concerns how different eras of the universe are linked by theory. It is the bridge between early and late descriptions that is under stress, not the behavior on either side. Precision has changed the nature of the question. It is no longer whether measurements are accurate. It is whether the assumptions connecting them are sufficient. When two correct methods yield incompatible answers, the problem lies in the framework that relates them. This is why the expansion rate disagreement has become a focal point. It does not demand abandonment of existing theory, but it does demand scrutiny of how those theories are combined. The deeper implication of this tension emerges when its persistence is examined. Discrepancies caused by overlooked errors typically diminish as data improve. This one has not. Each new measurement sharpens the disagreement rather than blurring it. That behavior is characteristic of a structural mismatch rather than an experimental flaw. What is being tested is the assumption that the same set of rules governs cosmic expansion uniformly from the earliest observable moments to the present day. That assumption has worked remarkably well across most observations. Precision now probes whether it works perfectly. The expansion rate disagreement is a direct challenge to that assumption. Resolving the tension requires altering some element of the connecting framework. That element could involve how energy components influence expansion, how matter behaves over vast distances, or how initial conditions are interpreted. Any such alteration must be subtle. It must preserve the extraordinary success of existing predictions while adjusting only what is necessary. Precision leaves no room for drastic change. This is why the problem has resisted simple explanation. There is little flexibility left. The framework is tightly constrained by data across many domains. The disagreement persists because the available degrees of freedom are nearly exhausted. Here, the operational definition of weakness becomes concrete. There is no failed prediction. There is no violation of observation. There is a point where a single theoretical structure cannot accommodate all verified measurements simultaneously without strain. The expansion rate disagreement does not reveal instability in the universe. It reveals the limits of a description that assumed smooth continuity across all scales and epochs. Precision has turned that assumption into a test it may not fully pass. As measurements continue to improve, this boundary will become sharper. Whether it leads to refinement or replacement remains open. What is certain is that it marks one of the clearest stress points in modern cosmology. When astronomers measure how matter moves in the universe, they encounter a persistent and quantitative discrepancy. The gravitational effects that are observed consistently exceed what can be produced by all visible matter combined. This excess is not subtle, localized, or rare. It appears across galaxies, across clusters of galaxies, and across cosmic history. The pattern is coherent, repeatable, and resistant to conventional explanation. The problem first becomes apparent when examining how stars orbit within galaxies. According to well-tested gravitational laws, orbital speed should decrease with distance once most of a galaxy's mass is enclosed. This expectation follows directly from equations that have been verified repeatedly within planetary systems and stellar binaries. Yet observations show something different. Stars far from galactic centers orbit at nearly constant speeds rather than slowing down. This behavior is not confined to a special class of galaxies. It appears in spiral galaxies of many sizes and compositions. The discrepancy is large. In many galaxies, the visible matter accounts for only a small fraction of the gravitational pull required to sustain the observed motions. Attempts to explain this by invoking unseen stars, cold gas, or observational error fail when applied systematically. The amount of ordinary matter required would conflict with independent measurements of radiation, chemistry, and stellar populations. Precision has eliminated these possibilities. The same pattern appears on larger scales. Galaxies within clusters move at velocities that far exceed what their combined visible mass can gravitationally bind. Without additional gravitational influence, these clusters would disperse over timescales far shorter than their observed lifetimes. Yet they remain intact for billions of years. This indicates that the discrepancy is not a peculiarity of individual galaxies, but a property of large-scale structure. Gravitational lensing provides an especially powerful line of evidence. When light from distant sources passes near massive objects, its path bends. The amount of bending depends only on the gravitational field, not on the composition or motion of matter. Measurements of lensing consistently reveal gravitational strength greater than what visible matter predicts. This method bypasses assumptions about how matter moves. It probes gravity directly. These observations do not depend on a single technique or instrument. They arise from independent measurements using different physical principles. Motion, binding energy, and light deflection all point to the same conclusion. There is more gravitational influence present than can be accounted for by luminous matter alone. The inference of missing mass is therefore not an assumption made to preserve theory. It is a conclusion forced by data. Something contributes gravitationally that does not emit or absorb light in detectable ways. Whether this contribution corresponds to new forms of matter or reflects limitations in gravitational description remains unresolved. What is not in question is the existence of the discrepancy itself. This problem does not arise from experimental uncertainty. It emerges because measurements are precise enough to rule out simpler explanations. The universe behaves consistently. The challenge lies in identifying what accounts for the gravity we observe. The strength of the missing mass problem lies not only in the size of the discrepancy, but in its coherence across methods, environments, and scales. When independent approaches converge on the same conclusion, the likelihood of coincidental error becomes vanishingly small. In this case, every major gravitational probe points in the same direction. There is a systematic excess of gravitational influence that cannot be attributed to known forms of matter. Attempts to eliminate the discrepancy by refining measurements have instead reinforced it. Improved distance, estimates, better modeling of stellar populations, and more complete inventories of interstellar gas have all reduced uncertainty without reducing the gap. Precision has tightened constraints rather than loosening them. The problem has become cleaner, not messier. One response has been to infer the existence of additional matter that interacts primarily through gravity. This inference preserves the form of gravitational law while extending the contents of the universe. Importantly, this unseen component is not arbitrary. Its distribution, abundance, and dynamical behavior are constrained by observation. It must cluster in ways that explain galaxy rotation curves, stabilize galaxy clusters, and influence the growth of structure over cosmic time. Large-scale simulations incorporating such unseen matter reproduce many observed features of the universe with remarkable fidelity. The web-like distribution of galaxies, the relative abundance of clusters, and the timing of structure formation all align closely with observation, when this additional gravitational component is included. This success strengthens the case that something beyond visible matter is influencing cosmic evolution. At the same time, this interpretation remains incomplete. Despite extensive experimental effort, no direct detection of such matter has yet been confirmed. Laboratory searches, underground detectors, and high-energy collisions have not produced unambiguous signals. The absence of detection does not rule out the hypothesis, but it constrains its properties increasingly tightly. An alternative response considers whether gravity itself behaves differently under certain conditions. In this view, the discrepancy does not arise from missing matter, but from an incomplete understanding of gravitational dynamics at very low accelerations or large scales. Any such modification must reproduce the extraordinary success of existing gravitational theory in regimes where it is well tested, while diverging only where discrepancies appear. This requirement is severe. Gravity has been confirmed with high precision in planetary systems, binary stars, and relativistic environments. Any modification must leave all of these results intact. Many proposed alterations fail this test. They may explain galaxy rotation curves, but struggle with lensing, cluster dynamics, or cosmological observations. Precision narrows the space of viable alternatives. What emerges is not confusion, but constraint. The missing mass problem is defined not by lack of ideas, but by lack of flexibility. Observation has limited the range of explanations to a small and demanding set. The unresolved status of the missing mass problem places it at one of the most restrictive boundaries in modern physics. No proposed explanation can succeed locally. It must succeed everywhere. Any account of the discrepancy must explain galaxy rotation, cluster stability, gravitational lensing, and large-scale structure simultaneously, without disrupting the many predictions that already work with high precision. This requirement eliminates most simple solutions. If unseen matter exists, it is not a minor correction. It dominates the mass content of the universe. Ordinary matter makes up only a small fraction of the total gravitational influence inferred from observation. This unseen component would therefore shape cosmic history from its earliest moments, guiding how matter clumped, how galaxies formed, and how large-scale structure emerged. Its properties would not be peripheral. They would be foundational, yet the lack of direct detection remains significant. Precision experiments have not been idle. They have explored wide ranges of possible interaction strengths, masses, and behaviors. Each null result tightens constraints. The unseen matter, if it exists, must be increasingly elusive in how it interacts with known particles. This does not invalidate the inference. It clarifies its character. If unseen matter does not exist, the alternative is equally demanding. Gravity itself would require modification in regimes that have not yet been directly tested. Such a modification would need to be subtle, scale-dependent, and consistent with all existing conformations of gravitational law. It would need to explain why deviations appear only in certain contexts and not others. This is not impossible, but it is highly constrained. What makes the missing mass problem especially revealing is that it cannot be isolated. It connects to other tensions in cosmology and fundamental physics. Any change to gravity influences cosmic expansion. Any new matter influences early universe behavior. Precision ties these domains together. A solution in one place must propagate consistently everywhere else. This interconnectedness transforms the problem into a structural one. It is not about filling a gap in observation. It is about integrating a missing component into a framework that is already tightly bound by data. There is little room for arbitrary adjustment. Every change is felt globally. Here, the operational definition of weakness applies with clarity. The universe behaves consistently across all observed scales. There is no anomaly in nature's behavior. The weakness lies in our current inability to provide a single description that accounts for all verified gravitational phenomena without additional assumptions. As observations continue to improve, this pressure will not diminish, it will sharpen. Whether the resolution lies in new constituents of matter or in revised gravitational principles, the missing mass problem marks a boundary where existing descriptions reach their limit. It is not a failure of observation. It is not a contradiction of law. It is a sign that something essential remains unaccounted for in how gravity and matter are described together. One of the most precisely established facts about the universe is that its expansion is accelerating. This conclusion does not rely on a single observation or a single method. It emerges from multiple, independent measurements that probe how the rate of cosmic expansion has changed over time. Distant stellar explosions appear systematically dimmer than expected in a universe whose expansion is slowing. Large-scale structure evolves in a way that favors accelerated expansion. Measurements of relic radiation are consistent with a persistent energy component that affects the geometry of space itself. These lines of evidence converge on the same result. The acceleration is not attributed to a force in the conventional sense. It is attributed to energy associated with empty space. Vacuum energy enters the equations of cosmic expansion as a uniform contribution that does not dilute as the universe grows. Its influence is subtle but cumulative. Over billions of years, it comes to dominate the dynamics of expansion. The value required to match observation is small, but precisely constrained. Here, the theoretical tension becomes unavoidable. Quantum field theory, which successfully describes the behavior of particles and fields with extraordinary accuracy, predicts that empty space should contain energy. This energy arises from unavoidable quantum fluctuations that persist even in the absence of particles. The calculation is not exotic. It follows directly from the same principles that correctly predict measurable effects in laboratories. When this vacuum energy is calculated using standard methods, the result is enormous. The predicted energy density exceeds the observed value by a factor so large that ordinary language struggles to convey it. The discrepancy spans many orders of magnitude. It is not a difference of degree, it is a difference of kind. This mismatch is not the result of experimental uncertainty. The observed value of vacuum energy is constrained by multiple, independent cosmological measurements. Adjusting it significantly would destroy agreement with data describing expansion history, cosmic structure, and radiation patterns. The number is not flexible, it is fixed by observation. At the same time, the theoretical calculation is not easily dismissed. Quantum field theory does not allow vacuum energy to be arbitrarily set to zero. The contributions arise inevitably from the structure of the theory itself. Removing them without consequence would undermine predictions that have been confirmed with extraordinary precision elsewhere. The same mathematics that overshoots cosmological observation succeeds spectacularly in particle physics. This is why the vacuum energy problem is described as a mismatch rather than a mystery. Both sides of the comparison are robust. Both are supported by data, yet they cannot be reconciled within the current framework without introducing extreme and unexplained cancellation. Such cancellation is mathematically possible, but physically unmotivated. Any slight imbalance would reintroduce effects that are not observed. The severity of the discrepancy elevates it beyond ordinary theoretical tension. In most cases, disagreement signals missing corrections or incomplete modeling. Here, the scale of disagreement overwhelms such explanations. No small adjustment bridges the gap. Precision eliminates the possibility that the difference hides in uncertainty. What makes this especially revealing is where the problem sits. Vacuum energy lies at the intersection of quantum theory and gravity. It is where quantum behavior is asked to influence space-time geometry directly. Both frameworks work extraordinarily well on their own. Their combination produces a result that reality does not support. This does not imply that empty space behaves unpredictably. The observed acceleration is smooth, stable, and consistent across cosmic time. The universe expands in a controlled and measurable way. What fails is the attempt to describe that expansion using theoretical tools that were never designed to operate together without modification. The vacuum energy problem is therefore technical in the strictest sense. It arises from a numerical conflict between established calculation and established measurement. It does not depend on interpretation or philosophy. It is a direct comparison of numbers that refuse to agree. Nothing in this situation suggests that physical law is breaking. The universe shows no instability. It follows clear dynamical rules. The weakness lies in our current description of how quantum fluctuations contribute to space-time curvature. Precision has exposed a structural incompatibility. As observational constraints tighten and theoretical understanding deepens, this mismatch does not fade. It becomes sharper, and in that sharpening, it marks one of the clearest boundaries of present understanding. The magnitude of this mismatch is what sets it apart from nearly every other problem in modern physics. In most theoretical disputes, disagreement spans a modest range. A factor of 2, 10, or even 100 can often be traced to missing effects, overlooked interactions, or limitations of approximation. Here, the gap is so vast that conventional reasoning fails. Theoretical expectation exceeds observation by an amount that cannot be absorbed, hidden, or renormalized away without consequence. What makes this especially troubling is that the calculation of vacuum energy uses the same mathematical machinery that succeeds everywhere else. Quantum field theory predicts particle masses, interaction strengths, and scattering outcomes with precision that has been confirmed to extraordinary accuracy. The same framework underlies technologies that function reliably every day. Its validity within its tested domain is not in question. Yet when that framework is asked to describe the gravitational influence of empty space, it produces a result that is catastrophically wrong. Not slightly wrong, not directionally wrong. Wrong by an amount that would render the universe violently unstable if it were realized. The fact that the universe is instead calm, long-lived, and structured places a severe constraint on explanation. Attempts to resolve this mismatch often involve cancellation. Large positive and negative contributions to vacuum energy could, in principle, sum to a small net value. Mathematically, this is allowed. Physically, it is deeply problematic. Such cancellation would require balancing terms with extreme precision, far beyond what any known mechanism enforces. Any tiny deviation would lead to observable effects that are not seen. Precision makes this explanation brittle. The difficulty is not merely aesthetic. Fine cancellation introduces instability. If the balance is not protected by a deeper principle, it becomes sensitive to changes in energy scale, environmental conditions, or quantum corrections. Maintaining such balance across cosmic history would require an explanation more complex than the problem it solves. Precision again tightens the constraint. It is also important to recognize what the vacuum energy problem does not depend on. It does not rely on speculative observations or poorly constrained data. The accelerated expansion of the universe is established through independent lines of evidence that reinforce one another. Removing vacuum energy entirely would conflict with observation. Increasing it significantly would also conflict. The allowed value occupies a narrow and well-defined range. This places theory in an uncomfortable position. It must explain why vacuum energy exists, why it has the observed value, and why quantum contributions appear not to gravitate in the naive way expected. Each of these requirements is individually demanding. Together, they form one of the most restrictive consistency conditions in modern physics. What is exposed here is not a flaw in quantum theory or in gravity taken separately. It is a limitation in how they are combined. Quantum field theory was developed on a fixed background. Gravitational theory treats the background as dynamic. Vacuum energy forces these perspectives into direct interaction. Precision has made that interaction unavoidable. The result is not contradiction, but incompatibility of expectation. Reality selects a value that theory does not naturally produce. The universe behaves smoothly. Our calculation does not. This is why the vacuum energy problem is regarded as structural. It signals that current theoretical architecture is missing an organizing principle that governs how quantum fluctuations influence space-time. Until that principle is identified, the mismatch remains. The persistence of this mismatch places strict limits on how it can eventually be resolved. Any proposed explanation must satisfy several conditions simultaneously. It must reproduce the observed acceleration of the universe with the correct magnitude. It must preserve the extraordinary success of quantum field theory in non-gravitational settings, and it must do so without introducing new instabilities or unexplained fine cancellation. Precision leaves no room to relax these requirements. This is why the vacuum energy problem has resisted solution for so long. It is not because ideas are lacking. It is because most ideas fail under constraint. Adjusting quantum theory risks breaking predictions that have been confirmed to many decimal places. Modifying gravity risks undermining its success in describing cosmic structure and relativistic phenomena. Introducing new mechanisms often shifts the problem rather than removing it. Importantly, the observed value of vacuum energy is not zero. This eliminates an entire class of otherwise simple explanations. Whatever suppresses quantum contributions does not eliminate them entirely. It allows a small residue to remain, one that is dynamically relevant only on the largest scales and over the longest times. Explaining this selective influence is extraordinarily difficult. The problem, therefore, highlights a limitation in extrapolation. Quantum field theory was never experimentally tested in a regime where vacuum fluctuations gravitate directly. General relativity was never formulated to accommodate quantum zero-point energy without modification. Precision has now forced both frameworks into a domain where neither can operate alone. What fails here is not prediction in isolation, but synthesis. The universe demands a consistent account of how energy of all forms influences space-time curvature. Current theory provides two partial answers that do not align when combined. The mismatch is not philosophical. It is numerical, concrete, and measured. This is the operational meaning of weakness in this context. There is no observation that violates known law. There is no instability in cosmic behavior. The weakness lies in the inability of existing theoretical structures to accommodate all verified inputs simultaneously without extreme adjustment. As measurements improve and theoretical bounds tighten, the vacuum energy problem becomes more sharply defined rather than more mysterious. It marks a boundary where present descriptions reach their limit. Beyond that boundary, new structure is required, not to replace what works, but to explain why it works together. The universe offers no hint of breakdown. Its expansion is smooth, its structure coherent, its history consistent. The strain lies entirely in our attempt to describe empty space, using tools that were never meant to be unified without deeper principle. In this sense, the vacuum energy problem is not an embarrassment. It is a guidepost. It indicates precisely where understanding must deepen. And like every such boundary encountered before, it is revealed not by failure, but by success pushed to its extreme. Among all known physical interactions, gravity occupies a singular and stubborn position. It governs the motion of planets, the structure of galaxies, and the evolution of the universe itself. Its effects are familiar and pervasive, yet its theoretical status is fundamentally different from that of every other interaction. While electromagnetism and the nuclear forces are described within a unified quantum framework, gravity remains isolated, resistant to incorporation into that structure despite decades of effort. This isolation is not due to lack of mathematical sophistication or experimental motivation. It arises from a deep incompatibility between how gravity is described and how quantum theory is formulated. Quantum theory treats physical processes as occurring on a fixed background. Fields fluctuate, particles interact, and probabilities evolve against an underlying stage that is assumed to exist independently of the dynamics taking place upon it. Gravity does not permit this separation. In gravitational theory, the stage itself is dynamical. Space-time is not a passive arena. It responds directly to energy and momentum. This difference is not cosmetic. It reshapes the meaning of interaction. In quantum theories, forces are mediated by exchanges that occur within spacetime. In gravity, the effect is encoded in the geometry of spacetime itself. Matter and energy determine curvature, and curvature determines motion. There is no background left untouched by the interaction. Everything participates. When attempts are made to apply quantum procedures directly to this geometric description, problems arise immediately. Calculations produce infinities that cannot be removed by known techniques without destroying predictability. The usual methods that tame divergences in quantum field theory fail because gravity couples to energy universally. Every fluctuation contributes. There is no natural cutoff that preserves consistency. This failure is not subtle. It is not a matter of missing terms or incomplete calculation. It reflects a structural mismatch. Quantum theory assumes small fluctuations around a stable background. Gravity denies the existence of such a background. Precision exposes this conflict by forcing the two frameworks into contact in regimes where neither can dominate safely. Experiment reinforces this separation. Quantum effects of gravity are expected to become significant only at energies far beyond current experimental reach. No laboratory experiment has directly observed a quantum gravitational phenomenon. At the same time, precision tests of gravity confirm its classical behavior down to extremely small distances and low accelerations. Each framework succeeds completely where it is tested. Their isolation persists not because one fails, but because neither yields ground to the other. This matters because gravity interacts with everything. Any complete description of nature must allow gravity to coexist consistently with quantum matter. Without that consistency, predictions cannot be extended reliably into regimes where both effects are essential. The earliest moments of cosmic history, the behavior of extreme astrophysical objects, and the ultimate limits of measurement all depend on this unresolved relationship. Gravity is not weak in its consequences. It is isolated in its description, and that isolation defines one of the clearest boundaries of current physical theory. The consequences of gravity's isolation extend far beyond abstract theory. They define where present descriptions cease to provide reliable guidance. Whenever physical conditions approach regimes where both quantum effects and strong gravitational effects should matter simultaneously, existing tools lose coherence. Calculations can be performed, but their results depend sensitively on assumptions that cannot be independently justified. Precision, rather than resolving this ambiguity, sharpens it. One reason gravity resists quantization is tied to how it responds to energy. In quantum theory, probing smaller scales requires higher energies. This strategy has worked repeatedly for other interactions. Gravity turns this strategy against itself. Concentrating energy into a smaller region increases spacetime curvature. Beyond a certain point, the act of probing alters the geometry so strongly that it prevents access to the scale being examined. This is not a limitation of technology. It is a physical obstruction imposed by gravity's universal coupling. As a result, there is no smooth experimental path toward quantum gravity. Other forces can be explored incrementally by increasing energy or resolution. Gravity offers no such dial. Either its effects are negligible and quantum theory dominates, or its effects overwhelm and classical description takes over. The regime where both are equally important remains experimentally inaccessible. Precision deepens this divide by confirming the absence of intermediate behavior. The mathematical structure mirrors this problem. Quantum field theory relies on perturbation, treating interactions as small corrections to a fixed background. Gravity does not allow such expansion in a controlled way. Its equations are nonlinear at all scales. Small fluctuations in energy can lead to large geometric effects. This undermines the foundational assumption that makes quantum calculations tractable. Attempts to circumvent this difficulty by redefining variables or introducing auxiliary structures have not resolved the core issue. Each approach either sacrifices predictive power or reintroduces background assumptions indirectly. Precision tests then expose these weaknesses. What survives is not a unified theory, but a collection of partial descriptions whose domains do not overlap cleanly. It is important to emphasize what this situation does not imply. It does not imply that space-time behaves chaotically at small scales. It does not imply that gravity violates quantum principles. It implies only that existing formulations cannot be straightforwardly combined without contradiction. Each theory encodes a different notion of what is fundamental. This divergence becomes especially significant when gravity's universality is considered. Every form of energy and information contributes gravitationally. Any inconsistency in how gravity is treated therefore propagates everywhere. There is no sector of physics that can remain untouched by a mismatch at this level. Precision has forced recognition of this fact. The isolation of gravity is no longer an abstract concern. It constrains how confidently existing theories can be extrapolated into extreme regimes. Where quantum and gravitational effects overlap, current descriptions offer no single, consistent answer. This is not failure, it is a boundary. And it is a boundary defined not by ignorance, but by the limits of synthesis under extreme precision. The physical significance of this boundary becomes clearest when considering why gravity's isolation cannot be ignored. Predictions about the earliest observable moments of the universe depend critically on the interaction between quantum fluctuations and space-time curvature. The formation of structure, the distribution of matter, and the imprint left on cosmic radiation all rely on assumptions about how these effects combine. Without a consistent framework, such predictions remain provisional. Similarly, the behavior of matter under extreme compression, such as in the densest astrophysical environments, pushes existing theory beyond its tested limits. Classical gravity predicts smooth geometry up to certain extremes. Quantum theory predicts fluctuations that challenge that smoothness. When both predictions apply simultaneously, current frameworks offer no unified account. Precision data can constrain outcomes, but interpretation remains limited. It is essential to distinguish between absence of description and presence of inconsistency. The universe does not behave unpredictably in these regimes. Observations remain consistent and reproducible. What is missing is a description that can incorporate all relevant effects at once without contradiction. This preserves the integrity of empirical science while acknowledging theoretical incompleteness. The isolation of gravity therefore serves as a diagnostic. It identifies where the assumption of separability breaks down. Space-time cannot be treated as a fixed stage when quantum effects become significant, and quantum fluctuations cannot be treated as mere perturbations when geometry itself is dynamic. Precision has turned this conceptual insight into a quantitative constraint. This does not mandate a specific solution. It does not demand unification by fiat. It demands consistency. Any future framework must reduce to existing theories where they are known to work, and must explain why gravity behaves classically under all tested conditions while remaining compatible with quantum principles at deeper levels. That is a narrow and demanding requirement. Here again, the operational definition of weakness applies. There is no violation of observation. There is no failure of prediction within tested domains. There is a regime where no single theoretical structure can yet account for all verified phenomena simultaneously. As experiments extend to more extreme environments and observations probe earlier cosmic epochs, this boundary will become sharper. The isolation of gravity will not disappear on its own. It will either be resolved by deeper structure or remain a defining limit of present understanding. What it signals is not instability in nature, but incompleteness in description. Gravity continues to shape the universe reliably and predictably. It is our attempt to integrate it fully with quantum theory that remains unfinished. Information occupies a role in modern physics that would have been unrecognizable a century ago. It is no longer treated as an abstract bookkeeping tool or a metaphor for knowledge. It is treated as a physical quantity, subject to conservation laws, transformation limits, and measurable constraints. This shift did not occur suddenly. It emerged from thermodynamics, statistical mechanics, and quantum theory, where information became inseparable from energy, entropy, and prediction. In thermodynamics, information determines how much work can be extracted from a system. Entropy does not measure disorder in a vague sense. It measures how much microscopic detail is hidden from macroscopic description. This interpretation has been confirmed experimentally. Reducing uncertainty about a system allows more useful work to be extracted. Increasing uncertainty limits what can be done. Information has direct physical consequences. Quantum mechanics sharpened this connection further. In quantum systems, information governs what can be known, copied, or erased. There are strict limits on measurement, communication, and computation that arise directly from quantum principles. These limits are not technological, they are enforced by the structure of the theory itself and have been confirmed in countless experiments. Information behaves as a conserved resource under allowed transformations. As understanding deepened, it became clear that information is not optional. It constrains physical processes just as energy does. This realization led to a profound question. If information is physical, then any fundamental description of the universe must explain how information behaves under all conditions, including extreme ones. Gravitational systems place these principles under exceptional stress. When matter collapses into highly compact configurations, entropy and information appear to follow rules, unlike those governing ordinary systems. In such regimes, the maximum information content of a region does not scale with volume, but with surface area. This result is not speculative. It emerges repeatedly from independent calculations that combine gravity, thermodynamics, and quantum reasoning. The importance of this scaling lies in its universality. It does not depend on the details of matter or interactions. It reflects a deep relationship between information and space-time geometry. Precision has confirmed that this relationship is not accidental. It appears wherever gravity becomes dominant. This creates a demanding consistency requirement. Quantum theory supports information conservation. Experiments confirm that information is not destroyed by physical processes. Gravitational theory imposes limits on how information can be stored and accessed. A complete framework must allow both to be true simultaneously. Progress has been made. Situations once thought to destroy information are now understood to redistribute it in subtle correlations. Information that appears lost becomes inaccessible rather than eliminated. This distinction preserves predictability in principle, even when recovery is impractical. Precision has resolved many apparent contradictions. What remains unresolved is not whether information is conserved, but how that conservation is enforced when space-time itself becomes dynamic. The universe appears to respect information limits under all observed conditions. The mechanisms that implement those limits at the intersection of gravity and quantum behavior remain only partially described. Information has therefore become a diagnostic. It reveals where current theory works seamlessly and where it reaches its boundary. It does not expose inconsistency in nature. It exposes incompleteness in description. The tension surrounding information does not arise from contradiction, but from the conditions under which information must be tracked. In ordinary quantum systems, information can be followed precisely through well-defined degrees of freedom. Measurements, interactions, and evolution preserve information even when it becomes highly distributed. Laboratory experiments repeatedly confirm this behavior. Information is not destroyed, it is transformed. Gravitational systems complicate this picture because they alter the structure through which information flows. When space-time curvature becomes significant, familiar notions of localization break down. Information cannot be assigned cleanly to fixed regions or particles. The act of concentrating information requires energy, and energy curves space-time. Beyond certain limits, attempts to isolate information change the system so strongly that the original description loses validity. These limits are not paradoxes. They are physical constraints. There are bounds on how much information can be stored in a given region and how quickly it can be processed or transmitted. These bounds arise from combining quantum principles with gravitational dynamics. They do not depend on speculative assumptions. They emerge from well-tested laws applied consistently. At the same time, experiments continue to show that information is remarkably resilient. Even when systems thermalize or appear to lose structure, information persists in correlations that are difficult to access but not erased. The difference between loss and inaccessibility is crucial. Physics requires only that information be preserved in principle, not that it remain practically retrievable. The difficulty lies in describing these processes with a single coherent framework. Quantum theory tracks information through abstract state spaces. Gravitational theory tracks geometry and energy through space-time curvature. When both descriptions are required simultaneously, neither alone is sufficient. Precision exposes where their overlap remains incomplete. This does not undermine predictability in ordinary conditions. It defines where predictability must be qualified. Information behaves consistently, but the pathways through which it is encoded and redistributed under extreme conditions are not yet fully captured by existing theory. The universe respects information limits. What remains open is how those limits are enforced when the very fabric that carries information becomes dynamic. The remaining gap concerns enforcement rather than principle. All available evidence supports the conclusion that information is conserved in physical processes. No experiment has demonstrated fundamental information loss. What remains unclear is how this conservation is implemented when space-time itself becomes an active participant rather than a passive background. The laws appear to hold, but the bookkeeping becomes subtle and demanding. This subtlety matters because information underlies causality and prediction. If information could be destroyed, physical evolution would lose reversibility, even in principle. Deterministic laws would cease to guarantee consistent outcomes when traced backward. Observations strongly disfavor this possibility. Instead, what occurs is degradation of accessibility. Information becomes dispersed across many degrees of freedom, encoded in correlations that are practically unreachable, but theoretically present. Precision has narrowed the scope of uncertainty. Earlier concerns suggested outright contradiction between gravitational behavior and information conservation. Those concerns have been resolved. Careful analysis shows that apparent loss arises from incomplete accounting rather than physical destruction. This resolution represents genuine progress. It demonstrates that the universe respects consistency even under extreme conditions. What remains is a technical gap in description rather than a logical inconsistency. Current frameworks lack a unified language that can describe how information flows when geometry, energy, and quantum states all evolve together. Quantum theory alone is insufficient because it assumes fixed structure. Gravitational theory alone is insufficient because it does not track microscopic information. Precision has forced recognition of this limitation. Information, therefore, occupies a role similar to energy in earlier stages of physics. Once treated as an abstract concept, energy became concrete through conservation laws and experimental verification. Information has now reached a comparable status. It constrains what transformations are possible, how systems evolve, and what predictions can be made. It is not optional. It is enforced by nature. This realization reframes the remaining challenge. The question is not whether information is fundamental. It is how fundamental information is implemented when space-time itself participates dynamically. Answering that question requires a framework that treats information, geometry, and quantum behavior on equal footing. Here again, the operational definition of weakness applies. There is no violation of observation. There is no breakdown of law. There is a domain where existing descriptions cannot yet express all verified constraints simultaneously without strain. As measurements improve and theoretical bounds sharpen, information continues to act as a guidepost. It highlights where our current descriptions succeed and where they must be extended. It does not reveal instability in the universe. It reveals the edge of our present understanding. That edge is not a failure. It is the frontier where deeper structure must emerge. Physical law is often spoken of as if it guarantees foresight. If the equations are known and the initial conditions are specified, the future appears fixed, at least in principle. This intuition has deep historical roots and is supported by many successful predictions. Yet modern physics reveals a more constrained picture. Even when laws are fully deterministic and perfectly specified, prediction itself can encounter fundamental limits that no increase in skill, technology, or data can overcome. These limits do not arise from ignorance of rules. They arise from the structure of the systems governed by those rules. In many physical contexts, extremely small differences in initial conditions grow rapidly with time. Two states that begin almost identically evolve into outcomes that diverge dramatically. This behavior is not hypothetical. It has been measured repeatedly in laboratory systems, planetary motion, fluid dynamics, and atmospheric processes. The equations remain exact. What fails is the ability to specify initial conditions with infinite precision. Precision, paradoxically, intensifies this problem rather than resolving it. As measurements become more accurate, the demand placed on initial information grows faster than experimental capability can supply. In sensitive systems, reducing uncertainty by a small factor requires exponentially greater resolution. Beyond a certain point, further refinement is not merely impractical, it is physically impossible. Information itself becomes the limiting resource. This limitation is enforced by fundamental constraints. Every measurement extracts information through interaction. That interaction requires energy. Energy disturbs the system being measured. There is no way to observe without influence. Physics does not permit unlimited extraction of detail without cost. These trade-offs are not philosophical. They are codified in experimentally verified principles that limit how precisely complementary properties can be known simultaneously. Cosmic scale phenomena amplify these constraints. Observers occupy a finite region of spacetime with limited causal access. Signals propagate at finite speed. The expansion of the universe places horizons beyond which information cannot be retrieved, even in principle. No observer can access complete data about the global state of the universe. Predictions about regions beyond observable boundaries rely on extrapolation rather than direct verification. Importantly, this does not introduce subjectivity. The universe does not change behavior based on who observes it. Physical processes unfold according to consistent laws everywhere. What changes is the operational meaning of prediction. A prediction is only meaningful if it can, in principle, be tested or constrained by accessible information. Beyond that boundary, statements lose physical content. These limits apply even in classical systems. Deterministic equations do not guarantee long-term predictability. They guarantee only that evolution is well-defined given exact information. When exact information is physically inaccessible, predictability degrades despite determinism. This distinction is essential. Unpredictability does not imply randomness. It implies bounded resolution. Information theory formalizes this insight. There are limits to how much information can be stored in a region, how quickly it can be processed, and how reliably it can be transmitted. These limits depend on energy, entropy, and gravity. They are not technological barriers that can be overcome with better instruments. They are physical constraints enforced by nature itself. In gravitational contexts, these limits become especially strict. Concentrating information requires concentrating energy. Concentrating energy curves space-time. Beyond certain thresholds, attempts to encode more information alter geometry so strongly that the original encoding breaks down. Prediction fails not because laws change, but because the system can no longer support arbitrarily fine detail. None of this weakens physics. It clarifies its domain. Laws describe relationships. Predictions require information. When information is bounded, prediction inherits that bound, even if the law remains exact. Precision reveals this boundary rather than erasing it. The limits of predictability are therefore not defects, they are features. They define where physical description remains meaningful and where it must give way to statistical or probabilistic accounts. The universe remains lawful. Our access to its exact state does not. These limits are measurable. They influence weather systems, orbital dynamics, quantum experiments, and cosmic evolution. They shape what can be forecast, how far ahead, and with what confidence. They do not signal failure of determinism. They signal completion of it under physical constraint. Understanding these limits reframes expectation. Physics does not promise omniscience. It promises consistency within boundaries imposed by information, energy, and space-time. Precision has made those boundaries visible. The consequences of bounded predictability become clearer when examined across different physical regimes. In systems governed by simple equations and weak sensitivity, prediction can remain accurate for long periods. Small uncertainties grow slowly, allowing forecasts to remain reliable. In contrast, systems with strong sensitivity amplify uncertainty rapidly. In these systems, prediction horizons shrink dramatically, even when the governing laws are fully known. This behavior is not rare. It appears in fluid flow, plasma dynamics, orbital motion involving many bodies, and even in certain quantum systems, when many degrees of freedom interact. In each case, the equations of motion are deterministic. The unpredictability arises because the amount of information required to specify the system's state with sufficient accuracy exceeds what can be physically obtained or stored. Precision does not remove this limitation, it sharpens it. As experimental resolution improves, it reveals how quickly uncertainty propagates. Attempts to extend prediction further demand exponentially more information. At some point, the required information exceeds physical bounds. No apparatus can encode it. No measurement can extract it without disrupting the system itself. This leads to an important distinction between mathematical determinism and physical predictability. Determinism refers to the existence of well-defined evolution rules. Predictability refers to the ability to use those rules to forecast outcomes. The first can hold while the second fails. Physics confirms this distinction repeatedly. Laws can be exact while prediction remains limited. Causality remains intact throughout this process. Effects still follow causes. There is no violation of temporal order. What is lost is resolution, not connection. Outcomes remain determined, but they cannot be resolved beyond a certain precision horizon. This preserves the logical structure of physical law while acknowledging practical and fundamental limits. In cosmology, these limits are unavoidable. The observable universe represents only a portion of the whole. Beyond that region, initial conditions are inaccessible. Even within the observable domain, information from early times has been partially erased or scrambled by expansion, interactions, and gravitational dynamics. Predictions about global behavior therefore rely on statistical inference rather than direct specification. Statistical description is not a retreat, it is an adaptation. When exact states cannot be known, physics describes ensembles rather than trajectories. This approach has proven extraordinarily successful, from thermodynamics to quantum mechanics to cosmology. It reflects not ignorance, but respect for information limits. Importantly, statistical laws are not weaker than deterministic ones. They encode constraints that are more robust precisely because they do not depend on inaccessible detail. Precision reinforces this approach by showing where detailed prediction is impossible and where probabilistic structure remains reliable. These considerations also clarify what predictability does not depend on. It does not depend on consciousness, observation in a psychological sense, or philosophical interpretation. It depends on measurable constraints imposed by energy, entropy, and space-time. Every observer, regardless of perspective, faces the same limits. Thus, The limits of predictability are not contingent. They are universal. They arise wherever physical law interacts with finite information. Precision has not eliminated uncertainty. It has revealed its unavoidable origin. The final implication of bounded predictability is that it defines a hard edge to what physical explanation can demand. Beyond this edge, asking for more detail ceases to be meaningful because the universe itself does not supply the information required to answer. This is not a failure of theory, computation, or imagination. It is a physical limit imposed by how reality stores and transmits information. This limit reshapes how laws are interpreted. A law does not promise unlimited foresight. It promises internally consistent evolution, given information that can physically exist. When that information cannot exist, prediction cannot be extended, regardless of how exact the law may be. Precision does not weaken this conclusion. It enforces it. In many contexts, this boundary appears as a horizon. In chaotic systems, it appears as a timescale, beyond which trajectories diverge beyond resolution. In cosmology, it appears as a causal boundary beyond which information cannot reach an observer. In quantum systems, it appears as limits on simultaneous knowledge and control. These are not separate phenomena. They are expressions of the same underlying constraint. Crucially, these limits do not accumulate gradually into failure. They appear abruptly when thresholds are crossed. Below the threshold, prediction improves smoothly with precision. Above it, additional precision yields no gain. This behavior is a hallmark of fundamental limitation rather than technical inadequacy. Nature does not offer diminishing returns indefinitely. It enforces cutoffs. This has consequences for how theories are evaluated. A theory is not incomplete because it cannot predict beyond physical limits. It is incomplete only if it predicts where prediction is impossible. Modern physics increasingly respects this distinction. It does not seek omniscience. It seeks internally consistent boundaries. These boundaries also protect physical law from misuse. They prevent extrapolation beyond testable regimes. They restrict claims to what can be operationally defined. Precision plays a central role here. By tightening constraints, it reveals where extrapolation becomes unjustified. Prediction is no longer extended by assumption. It is extended only where information allows. This perspective resolves a common misconception. Limits on predictability do not undermine determinism where determinism applies. They do not introduce randomness where none exists. They simply separate the concept of lawful evolution from the ability to resolve that evolution in detail. Confusing these two leads to false expectations. The universe does not owe observers infinite resolution. It provides structure, regularity, and constraint. Within those constraints, physics operates with extraordinary success. Beyond them, description transitions naturally from trajectory to distribution, from certainty to probability. This transition is not arbitrary. It is dictated by physical limits. As measurement continues to advance, these boundaries will become more sharply defined. They will not retreat. Precision does not push the horizon outward indefinitely. It brings the horizon into focus. It tells us exactly where prediction ends and why. This is why the limits of predictability do not represent a weakness in physics. They represent a completion of its scope. They define what physical explanation can justifiably claim and where it must stop. That stopping point is not ignorance. It is fidelity to what the universe permits. In this sense, predictability ends not because law dissolves, but because information does. The laws remain intact. The universe continues to evolve consistently. What ends is our ability to specify outcomes beyond physically meaningful resolution. Recognizing this boundary is not a concession, it is a refinement. It ensures that physics remains grounded in what can be measured, constrained, and tested. Precision has not revealed chaos beneath order. It has revealed order with limits. Those limits are not optional. They are woven into the fabric of space-time, energy, and information, and acknowledging them is not the end of explanation. It is what allows explanation to remain honest. Modern physics does not claim that its laws apply uniformly, unchanged, and without qualification across all scales, energies, and conditions. Instead, one of its most deeply established insights is that many laws are effective. They describe reality accurately within specific domains, under specific constraints, and within ranges that have been experimentally tested. This is not a philosophical position. It is an empirical conclusion drawn from how physical descriptions behave when pushed beyond their proven limits. An effective law is not a rough guess or a temporary placeholder. Within its domain, it can achieve astonishing precision. The equations governing fluid motion predict turbulence, pressure, and flow with extraordinary accuracy without referencing atomic structure explicitly. Thermodynamics predicts heat transfer and equilibrium behavior without tracking individual particles. Classical mechanics predicts planetary motion to high precision without invoking quantum effects. These laws work not because they are fundamental, but because they capture exactly what matters at the scale where they are applied. This scale dependence is not optional. It is observed. When systems are examined outside the conditions under which a law was formulated, deviations appear. Classical mechanics fails at very high speeds and very small scales. Quantum mechanics becomes negligible for large objects under ordinary conditions. Relativistic corrections matter only when gravity is strong or velocities approach that of light. Each framework emerges from deeper structure while remaining valid where it has been tested. The danger arises when effective laws are treated as absolute. Mathematical expressions can be extended far beyond their experimental support, producing results that appear internally consistent but lack physical meaning. Precision now probes regimes where such extrapolations are no longer safe. Early universe conditions, extreme densities, and cosmic scale. Phenomena expose where assumptions embedded in effective theories begin to strain. This is not a recent discovery. Physics has always progressed by identifying the limits of its laws. What has changed is how sharply those limits are now defined. Precision measurements have reduced uncertainty to the point where mismatches between domains cannot be ignored. Where two effective descriptions overlap, they must agree. Where they do not, the overlap marks a boundary rather than a contradiction. Importantly, this does not imply that reality itself changes rules arbitrarily. The universe does not behave one way at one scale and randomly differently at another. The underlying structure remains coherent. What changes is which description captures that structure accurately. Effective laws are layers of description, each optimized for a particular regime. This layered structure explains why physics can be both extraordinarily accurate and visibly incomplete at the same time. Within their domains, effective laws deliver predictions that match observation to remarkable precision. Beyond those domains, they offer no guarantee. Precision has made this distinction unavoidable. The recognition that laws are effective reframes modern tensions. When descriptions fail to align across scales, the issue is not that law has broken. It is that applicability has been exceeded. Precision transforms this from a conceptual caution into a measurable constraint. Effective laws, therefore, do not weaken physics. They define its strength. They allow complex reality to be understood without tracking unnecessary detail, while also signaling clearly when deeper structure is required. The power of effective laws lies in their ability to compress reality without distorting it. They discard details that do not influence observable outcomes at a given scale, while preserving the relationships that do. This compression is not arbitrary. It is justified empirically. When ignored details truly do not matter, prediction improves rather than degrades. Effective laws succeed because they are economical, not because they are incomplete by accident. The limitation appears only when conditions change. Parameters that were once irrelevant re-enter influence. Degrees of freedom that were safely averaged out become dynamically important. Precision is what reveals this transition. As experiments probe new regimes, they expose where the assumptions underlying an effective description cease to hold. The law does not fail, its scope does. This transition is especially clear when comparing early universe physics with late universe physics. Many equations used to describe cosmic expansion, structure formation, and matter behavior today are extensions of models calibrated under vastly different conditions. For most of cosmic history, these extensions work extremely well. Precision now probes whether they work perfectly. In the earliest measurable moments, assumptions about equilibrium, smoothness, and separability may no longer apply. What once could be ignored now leaves a measurable imprint. This does not invalidate effective laws. It confirms their proper role. A law that is effective within a domain remains correct within that domain, even if it fails elsewhere. The mistake is not in using effective descriptions. It is in assuming they are universal. Physics advances by identifying where transitions occur and by constructing new descriptions that reduce to old ones when conditions allow. Scale dependence does not imply relativism or arbitrariness. The same underlying reality exists at all scales. What changes is the resolution required to describe it faithfully. Effective laws are connected through overlap regions where multiple descriptions apply simultaneously. In those regions, consistency is not optional. It must be demonstrated quantitatively. When overlap succeeds, confidence deepens. When overlap fails, the failure is informative. It marks where a missing layer of description must exist. Precision transforms this marking from a qualitative suspicion into a quantitative demand. The mismatch is no longer philosophical, it is measurable. This is why modern theoretical tension often appears at boundaries between regimes. It is not because physics lacks rules. It is because rules derived for one scale are being stretched to cover another. Effective laws resist such stretching. They signal their limits through inconsistency. Importantly, this resistance is constructive. It prevents overextension. It protects physics from making claims that cannot be tested or justified. Precision enforces discipline by revealing exactly where extrapolation becomes unreliable. Effective laws therefore act as both tools and warnings. They enable extraordinary predictive success while also defining where deeper explanation is required. They do not dissolve into ambiguity. They sharpen structure. As measurements continue to improve, these overlap regions will become more constrained. The space in which effective descriptions can coexist without deeper unification will shrink. This is not a crisis. It is the natural consequence of precision closing loopholes. The final implication of treating physical laws as effective rather than absolute is methodological discipline. Physics must distinguish clearly between where a description has been validated and where it is merely assumed. Precision has made this distinction unavoidable. Extrapolation without constraint no longer survives contact with data. Historically, every major advance in physics followed this pattern. Laws that appeared universal were later revealed to be scale-bound. Classical mechanics did not fail everywhere. It failed only where its assumptions were violated. Quantum mechanics did not replace classical physics. It refined it by specifying where classical description emerges and where it breaks down. Each transition preserved what worked while redefining scope. What precision has changed is the sharpness of these transitions. Boundaries that were once inferred qualitatively are now measured quantitatively. The overlap between descriptions is no longer broad and forgiving. It is narrow and demanding. Where two effective laws must agree, they are forced into direct numerical comparison. Any mismatch becomes a concrete problem rather than a philosophical concern. This is why modern tensions cluster at interfaces. Early universe versus late universe behavior. Quantum behavior versus gravitational dynamics. Microscopic information versus macroscopic geometry. These are not failures of individual theories. They are tests of whether effective descriptions can be consistently stitched together into a larger framework. Crucially, Treating laws as effective does not mean that anything is allowed. Constraints remain strict. Symmetries, conservation principles, and empirical consistency severely restrict what forms a deeper theory can take. Effective laws do not grant freedom. They impose structure by demanding that any deeper description reduce to them in the appropriate limits. This requirement is powerful. It ensures continuity of explanation across scales. A deeper theory cannot discard what works. It must explain why it works. Precision enforces this requirement mercilessly. Any proposed extension that fails to reproduce known results is immediately excluded. The danger lies in ignoring effectiveness. When a law is assumed to be absolute, discrepancies are misinterpreted as anomalies or failures, rather than signals of limited scope. This leads to confusion rather than progress. Recognizing effectiveness reframes inconsistency as information. It tells us exactly where assumptions must be revised. This perspective also clarifies the meaning of unity in physics. Unity does not require a single equation to describe everything at all scales. It requires that descriptions across scales fit together without contradiction. Effective laws are the pieces of that structure. Their overlaps define where unity must be demonstrated. Precision has brought physics to a stage where these overlaps dominate. Theories are no longer tested in isolation. They are tested in combination. The demand is no longer local accuracy, but global coherence. This is a higher standard than any previous era faced. Here, once again, the operational definition of weakness applies. There is no observation that contradicts physical law. There is no collapse of predictability within tested domains. There is a boundary where current descriptions cannot yet be unified without additional structure. That boundary is not a flaw in nature. It is a feature of how understanding grows. Effective laws are not provisional because they are uncertain. They are provisional because they are precise. Their precision exposes exactly where deeper explanation is required. As measurement continues to improve, these boundaries will not disappear. They will become more sharply defined. Effective laws will remain indispensable, but their limits will become increasingly visible. This is not the erosion of physics. It is its refinement. It is how a discipline moves from success within domains to coherence across them. And it is precisely at these boundaries, revealed by precision and enforced by consistency, that the next stage of understanding must emerge. At no point in this analysis has the universe shown any sign of instability, inconsistency, or failure. Every observation examined, from the motion of galaxies to the behavior of quantum systems, follows regular, repeatable patterns governed by precise relationships. The laws of physics continue to function with extraordinary reliability. What has emerged instead is a clear picture of where our current descriptions reach their limits. A weakness, defined operationally, is not a place where nature stops obeying rules. It is a place where our existing theoretical frameworks cannot simultaneously account for all verified observations without internal tension. This distinction is critical. It separates failure of reality from incompleteness of description. Modern physics confronts the latter, not the former. Historically, this situation is not unusual. Every major transition in physics began with success exposing limitation. Classical mechanics predicted planetary motion with astonishing accuracy, yet failed to account for electromagnetic phenomena and high-speed effects. That failure did not imply that planets behaved unpredictably. It implied that the scope of the theory had been exceeded. Precision revealed where deeper structure was required. The same pattern recurs throughout scientific progress. When thermodynamics encountered atomic behavior, when electromagnetism conflicted with classical time and space, when classical physics failed at microscopic scales, tension preceded synthesis. In each case, existing laws remained valid within their domains. What changed was the recognition that those domains were not universal. What distinguishes the present moment is the level of precision involved. Measurements now constrain theory so tightly that inconsistencies cannot be postponed or blurred. Independent observations probe different aspects of the same underlying reality, and demand numerical agreement. When that agreement fails, the problem is not aesthetic, it is structural. This structural nature explains why modern tensions resist quick resolution. They are not localized anomalies that can be patched without consequence. They involve the interfaces between frameworks that were developed separately and optimized for different regimes. Precision has forced those interfaces into direct comparison. Crucially, none of these tensions imply that physical law is provisional in the sense of being unreliable. They imply that physical law is layered. Each layer captures genuine aspects of reality under specific conditions. The challenge is not to discard these layers, but to understand how they emerge from a deeper, more general structure that preserves their success. This reframes the meaning of weakness entirely. A weakness does not mark a flaw in the universe. It marks a boundary of applicability. It tells us where explanation must deepen, rather than where it must retreat. Boundaries of this kind are not signs of decay. They are signs of maturity. Future observations will not resolve these issues by coincidence. They will resolve them by elimination. Precision will continue to shrink the space of viable explanations. Some ideas will be ruled out completely. Others will survive only by adapting to stricter constraints. This process is not speculative. It is how physics has always progressed. Importantly, falsifiability remains intact. Upcoming measurements of cosmic structure, gravitational behavior, and fundamental interactions have the capacity to invalidate entire classes of theoretical models. Physics has not retreated into ambiguity. It has advanced to a point where ambiguity is no longer tolerated. This demands restraint. Declaring resolution prematurely weakens understanding. Accepting incompleteness while demanding consistency strengthens it. The goal is not to defend existing theories at all costs, but to allow them to be tested where they are strongest and exposed where they are insufficient. In this sense, tension is productive. It identifies precisely where new structure is required without inventing it arbitrarily. It narrows the target. It replaces vague dissatisfaction with concrete constraint. The universe itself remains indifferent to these concerns. It evolves smoothly. Its structures persist. Its laws operate without exception across vast spans of space and time. There is no indication that reality itself is fragile or delicately balanced on the edge of failure. What remains provisional is our description, and that provisionality is not a weakness. It is the engine of progress. Every unresolved tension marks the frontier of understanding. It tells us not that something has gone wrong, but that something deeper remains to be discovered. The universe does not advertise its structure freely. It yields it only under relentless precision. This is what a weakness really signals. Not failure, not collapse, not instability, but the edge of knowledge reached by success pushed to its limit. And that edge is exactly where science has always advanced next. The presence of such boundaries is not an anomaly within science. It is an expected outcome when a discipline approaches the limits of what can be measured, constrained, and cross-checked. When precision reaches this level, theories are no longer insulated by approximation. Every assumption becomes visible. Every hidden dependency is exposed. What once appeared as a unified structure is revealed as an interlocking system whose joints are now under stress. What is striking about the current situation is not the number of open problems, but their character. Each tension arises where independently verified observations must be explained together rather than separately. Cosmic expansion, gravitational behavior, quantum dynamics, information conservation, and large-scale structure all work extraordinarily well within their respective domains. The challenge emerges only when a single framework is required to connect them all without contradiction. This requirement is new in its severity. In earlier eras, gaps between domains could be bridged loosely. Approximations were sufficient. Disagreements could be deferred. Precision now removes that option, a parameter adjusted to improve agreement. in one context immediately affects predictions elsewhere. Theoretical freedom collapses rapidly under this pressure. What remains is a narrow corridor of consistency. This is why unresolved problems in modern physics feel resistant rather than chaotic. They do not invite unlimited speculation, they restrict it. Each viable explanation must thread a path through an increasingly constrained landscape. Most possibilities fail, not because they are imaginative, but because they violate something already known with high confidence. In this sense, the current frontier is defined less by ignorance than by exclusion. Physics now advances by ruling things out with precision, rather than by proposing broad new frameworks unconstrained by data. This is a sign of maturity. It indicates that the structure of reality is being mapped tightly enough that errors cannot hide. Future observations will sharpen this process further. Measurements of cosmic structure, gravitational behavior, and fundamental interactions will continue to close loopholes. They will not guarantee resolution, but they will guarantee constraint. Models that survive will do so because they respect every verified relationship simultaneously, not because they explain a single anomaly in isolation. This is why claims of imminent revolution must be treated cautiously. Genuine progress at this stage is incremental and demanding. It requires preserving the extraordinary success of existing theories while extending their scope. That balance is difficult. Precision makes it unavoidable. Importantly, this situation preserves the core strength of physics. Falsifiability remains intact. Predictions remain testable. Disagreement is not tolerated indefinitely. Where theory and observation fail to align, theory must yield. What has changed is that yielding now occurs at the level of structure rather than at the level of individual predictions. This is a higher standard than physics has ever faced before. It demands not only accuracy but coherence. It demands that explanations agree across scales, regimes, and methods without exception. Precision enforces this demand relentlessly. Seen in this light, what appears as weakness is actually a refinement of criteria. Physics is no longer satisfied with local success. It demands global consistency. That demand exposes where current descriptions fall short, not because they are wrong, but because they are incomplete. This is how understanding deepens. Not by abandoning what works, but by discovering why it works so well where it does, and why it fails to extend seamlessly beyond those conditions. Precision transforms that discovery from intuition into requirement. The final synthesis follows directly from everything that precedes it. What modern physics has uncovered is not a single flaw, not a catastrophic inconsistency, and not a point where reality refuses to obey law. It has uncovered a pattern. Whenever observation becomes sufficiently precise, descriptions that once appeared unified reveal their seams. Those seams do not signal collapse. They signal where explanation must deepen. This pattern has repeated without exception throughout the history of science. Each time precision improved, it exposed limits that were invisible before. Each time, those limits were initially interpreted as problems. And each time, they ultimately became the entry point to deeper structure. Classical mechanics gave way to relativity and quantum theory, not because it failed broadly, but because it failed narrowly under exacting conditions. The same is true now. What is different today is scale. The tensions now appear not within a single domain, but at the interfaces between many domains at once. Gravity, quantum behavior, cosmic expansion, information, and effective description all intersect. Precision forces them into simultaneous consistency. That requirement is unprecedented. No earlier framework was ever asked to do so much at once. This explains why resolution has proven difficult. Any proposed extension must preserve an enormous body of verified knowledge while resolving only what is necessary. There is no room for sweeping change. There is only room for structure that is more general, more constrained, and more subtle than what came before. Precision has narrowed the path. This also clarifies why the universe itself shows no sign of weakness. There is no instability in cosmic evolution. No breakdown in predictability where prediction is meaningful. No evidence that physical law dissolves under scrutiny. The universe continues to behave with coherence across all observed scales. It is our descriptions that struggle to remain globally aligned. That distinction matters deeply. It preserves confidence in empirical science while acknowledging theoretical limits. It prevents confusion between failure of explanation and failure of reality. Modern physics faces the former, not the latter. A weakness, properly defined, is therefore not a defect. It is a diagnostic. It marks where assumptions embedded in our frameworks can no longer be maintained without qualification. It identifies where extrapolation has exceeded justification. It tells us precisely where new principles must enter, not arbitrarily, but under strict constraint imposed by everything that already works. This is not a crisis. It is the normal end state of successful theory. When a framework explains so much so accurately that only its boundaries remain problematic, it has done its job. It has mapped reality well enough to reveal where it no longer suffices. What comes next cannot be predicted in advance. History shows that deeper theories often look inevitable only in retrospect. What can be said with certainty is that any future advance will not discard the success of modern physics. It will explain it. It will show why current laws work as well as they do within their domains, and why they must be modified beyond them. Precision guarantees this outcome. As measurements continue to improve, the space of acceptable explanation will shrink further. The universe will continue to respond consistently. Our descriptions will be forced to adapt. That is not weakness. That is progress in its most demanding form. The universe has not revealed a flaw in itself. It has revealed the edge of our understanding. And history leaves little doubt about what happens next when such edges are reached.